by way of introduction, he's been at the Johnson Space Center since 1981. And he worked in the International Space Station program and on the NASA Mir program. I had to select other things from his resume. If I read his whole resume, we wouldn't have time for his talk. He's worked at the basic level of hardware, payloads, storage systems, crew on orbit support, computer systems, mechanical and electrical and data systems. He was the mission manager for the first space-had commercial missions. He has also worked on the space shuttle. He's been awarded the NASA Exceptional Achievement Medal, 2 Joint Space Center commendations, and the Silver Snoopy, which is presented by an astronaut for outstanding performance. And astronauts have a vested interest in outstanding performance. We've had, in our meetings here, we've had numerous talks about the findings in space. We had Margaret Geller on the cosmic web, friend Scott Kenyon these are from the Harvard Observatory, on star and planet formation. We've gone over the Pluto flyby. Charles Holbrow gave us lectures on the atmosphere of Venus. We've had lectures on Lagrange points. The one hardware, the helicopter on Mars. We've had images from the Hubble and James Webb Space telescopes, lecture on gravitational effects of celestial bodies, and some others. We really haven't had anything about how in the world we did it. So now we have Dr. Kitmacher to explain it all, the last 60 years of space exploration. And thank you, Dr. Kitmacher.
Okay, thank you for that introduction. I always enjoyed talking to people from my native state. I'm from Pittsfield up in Massachusetts. Haven't been up there in a little bit, but I always enjoy talking to folks from back home. I am going to talk a little bit about our current technology and where it came from, some of its origins. And I'm also going to talk somewhat today about what we are doing now and getting ready for the future. I'm glad to hear that you had a previous lecture on the Lagrangian points because one of the things I'll talk about today has a lot to do with putting it in an orbit that uses the Lagrangian points and going around the moon in a very distant orbit. We got here today over the course of the last really 75 years or so. That was an outgrowth of a program begun even earlier than the 1960s and the 1950s. When I talk about moon missions and the race to the moon, even before the Apollo race to the moon in the 1960s, there was another race to the moon going on in the 1950s, where both the Soviet Union and the US were trying to reach the moon with orbiters, with crash landers, even some attempts at soft landing. None of them worked very well. Russians had a lot more success than we did. Once we were able to build the hardware for Apollo, then we went to work trying to learn to live and work in space on board the first early space stations like Skylab. I was a participant in the Skylab. I was in high school at the time, and I had submitted an experiment that was done on Skylab to photograph the comet that was discovered at that time, Kohoutek. So the last astronauts who went to Skylab, Jerry Carr, Bill Pogue, and Ed Gibson were up there. And in fact, we kept them up there an extra month, during which they ran out of food and had to go on rations of granola bars, which they didn't forgive me for. I worked with them when we were early in the design of the space station. And more recently, over the last 30 years, we got involved in international partnerships, particularly with the Russians. I made a couple dozen trips over to Russia and worked on the Mir program. I actually had worked right out of college on Apollo Soyuz. I was a cartographer at the Smithsonian, and then I got to actually lead an effort on Mir to redesign one of the Russian modules as a U.S. laboratory. And we flew a lot of payloads, a lot of experiments, including some from MIT. I don't know if you know Dava Newman, who was the head of Astro Aero, and I think she now heads up the Media Lab. At one time, she was the assistant administrator at NASA, but we flew a payload of hers, the Enhanced Dynamic Load Sensor, first on shuttle and Space Hab in the early 1990s, and then we put it on Mir, and it was the first test of Wi-Fi, which the Russians did not like at all. The idea that someone would be using a radio signal inside their spacecraft, but we showed that it was fairly benign. And now we have new efforts ongoing that I'm going to talk a little bit about today with the International Space Station. First, to use the space station. Second, to try and commercialize low Earth orbit. And third, to get a group of nations together to go back to the moon and establish a permanent lunar base there. Now, when we look at how did we get to where we are, it really started a long time ago. You have to go back to the Renaissance, back really to Johann Kepler. Although before Kepler, there were people like Copernicus and Galileo. Copernicus, of course, said that the solar system and the Earth were not everything. Galileo looked at the different planets and said the planets were worlds. And then Johann Kepler, although he did not write this, he did not allow it to be published during his lifetime. He was afraid he would be believed to be a crackpot. And so once he died, this was published that one day people would be traveling in outer space, and we would recruit people who would be able to navigate the ships there. And so that's really the first signs that we would be having spaceflight programs. We started in the early 1960s with the Russians on Vostok and the Americans on Mercury one-man vehicles. The Mercury was only designed to last about a day in orbit. We had one flight that went beyond that, but all the systems had begun to break down. The Vostok actually had 1 week flights. And then, of course, we were getting ready to do 2-man flights in Gemini. And the first spacewalks, the first rendezvous and docking. And the Soviet Premier Khrushchev said his people needed to come up with something to once again outpace the Americans. And so they converted the Vostok into a multi-man spaceship called Voskhod, and flew first 3 men and then 2 men. They had plans for longer missions, but they were deferred in favor of a new vehicle that first flew in 1966 called Soyuz. And it kind of tells the story of the Russian program. Russians are still using Soyuz. They've upgraded it every now and then, but we still use it to get astronauts and cosmonauts from the Earth to the space station today. And then, of course, at the end of the 60s, we had a much more larger, more sophisticated set of vehicles, the Apollo Command Module and Lunar Module, and the astronauts landed on the moon beginning with Apollo 11. And a total of 6 pairs of astronauts, 12 people, landed there with the last mission, Apollo 17, in 1972. We started talking about a space shuttle in about 1968. And the main purpose was, number one, to continue human spaceflight, because there was real danger that without Apollo spaceships and without Saturn rockets, both of which had been turned off, that we weren't manufacturing anymore after 1966. The contracts were basically terminated. And so that was the first purpose, was to continue the space program, and second of all, to build a space station. Now, the idea of a space station goes back to the late 1800s, and there were a lot of ideas for space stations, including large wheel-shaped space stations, inflatable space stations, modular space stations. Once again, the Russians were told to win over the US, and so they quickly cobbled together Salyut 1, and it went up into orbit in 1971. It was operated successfully, although their 3 cosmonauts died when they returned because of an inadvertent pressure leak in the Soyuz capsule. So that was the first space station mission. The US had Skylab, and we had 3 missions of 1 month, 2 month, and 3 month duration. The Russians continued on with space stations, eventually developing an advanced station called Mir, which was made up of a series of the Salyut type modules attached together. And the last 2 modules of their station, which were Spectre right here and Perota, were modules that the US modified into laboratories. Spectre was never used very much because, number one, it was designed to be compatible with Spacelab, and Spacelab, which was flown on the shuttle, was too expensive. We stopped flying Spacelab, so the payloads weren't compatible. Perota, which I headed up over here, was designed to be compatible with the shuttle and with the Space Hab, which flew all the Mir missions. And so it was very successful, although very short-lived, because this module went into orbit in 1996, and the Mir program ended in 2000, and Mir crashed and burned up in the atmosphere in 2001. And all along, we were designing the International Space Station. I was heavily involved with International Space Station starting about the time of the Challenger accident. I was involved a little bit at the time with the accident investigation, but then I turned my attention to the modules of the space station. And so a lot of what we see today, we'll talk a little bit more about it, is the work that I was doing in the late 1980s. So in terms of the bigger picture, Salyut, Skylab were the first efforts at a space station. Mir was a more advanced version of a space station. And then the International Space Station today is the largest satellite ever orbited around the Earth. It was put up over the course of about 50 space missions, 35 space shuttle missions. It weighs about 1 million pounds, and we'll talk a little bit more about size and weight in just a moment. And where are we going with it from now? After the assembly of the space station, which was mostly complete in 2011, Space Shuttle was retired. And since that time, we've had a number of vehicles carrying cargo and crew to the space station. And that's because, according to US law, public law, NASA is supposed to be one of many customers of a low Earth orbit commercial human spaceflight enterprise. We want to maintain continuous human presence in orbit, but we want to transition to commercial platforms and services. The space station is still up there and operating, probably will continue to do so well into the 2030s. It's beyond its original design lifetime, but right now it is scheduled and budgeted to go to at least 2030, and there's no reason why it cannot continue beyond that. These 5 vehicles are the ones that have been in use or will be in use shortly. These are commercial vehicles. SpaceX Dragons, and that there have actually been three kinds of Dragons used for carrying cargo. The Northrop Grumman Cygnus spacecraft, which is actually developed based on the tooling from some of the earlier US modules. It's not manufactured in the US. The module is manufactured over in Italy. And then these two spacecraft on the right are new ones. Hopefully in a week or so, the Boeing Starliner Crew Space Transport 100, they call it, will go into orbit. It's had a long and tortuous history. The SpaceHab, or the SpaceX Crew Dragon, has been flying with astronauts now since 2020, actually going back to almost 2018. And these two were supposed to be flying about the same time. So SpaceX has been doing the yeoman's job. There have been 13 of the manned or crewed Dragon flights so far. 9 of those have been NASA flights, and 4 of them have been commercially paid for by private astronauts. And then a new space plane should be going into orbit perhaps later this year, called the Dream Chaser. It was originally designed to carry crew, but in the latest version, it's going to be carrying cargo initially. We expect the crew version will be online in a few years. When NASA was allocating budget for these commercial vehicles, they could only afford 2 at first. This was back in 2014. And they gave most of the money to Boeing. They felt Boeing stood the best chance of getting a vehicle into orbit soonest. And at that time, we were kind of in a critical situation because the shuttle had stopped flying. We needed the Starliner, the Boeing vehicle, to carry astronauts. We also gave money to SpaceX, but not nearly as much as we gave to Boeing. And Dream Chaser lost out. We had to not fund it initially. Later, when we had money to reissue a contract for cargo, the Dream Chaser won some money, and so they have been able to finish up with their efforts. And so the vision for a low Earth orbit economy is actually made up of a lot of different pieces. We have the commercial vehicles like from Northrop Grumman and SpaceX, Sierra Space, the Dream Chaser. We have some coming along, like from a company called Blue Origin, which is Jeff Bezos from Amazon. That is his company. But they are a little bit further behind. There are several people planning to put up a commercial space station. The idea would be that the commercial space station would replace the International Space Station. We don't know if there's really a customer base for that. One of our biggest problems has been in getting paying customers for the space station. So there's a lot of effort going into those currently. What are we doing on the space station? Well, we're testing out a lot of the systems for exploration in order to develop life support systems that can support crews for extended and indefinite durations. We're doing a lot of research, medical research, all kinds of research. I'll talk a bit more about it in a moment. It has been a main focus for international cooperation. We've had about 18 countries involved, 16 currently. Some countries come and go as they are able to support the program. but a lot of activity there, including not only the two prime stakeholders, which are Russia and the US. Europeans and Canadians and Japanese all have control centers, all have contributed main systems to the space station. And more, we are doing commerce. We are inviting in commercial customers to try and develop a space manufacturing base and support commercial activities in orbit. This is a brief video about the ISS.
This was once just a dream. What if we were to channel humanity's knowledge and creativity into something truly revolutionary? What if we built a bridge between and above all nations?
We have ignition and liftoff of the Soyuz rocket, beginning the first expedition to the International Space Station and setting the stage for permanent human presence in space.
To endeavor to live and to work outside our planet for the benefit of all within. What started as an accord between two former rivals became a beacon of opportunity for the rest of the world. We live this dream aboard the International Space
I
Station.
understand it's good to have you there and adjusting to your new home.
Adapting to life in space. It's been a process.
For the past 20 years, over 230 astronauts from all over the world have worked tirelessly together, boldly performing pioneering research and high-stakes spacewalks in the unforgiving environment of space. In this unparalleled orbital laboratory, circling the planet at 17,500 miles an hour, thousands of groundbreaking scientific experiments from over 100 countries have led to discoveries unachievable in the confines of Earth. From 250 miles up, an unbroken chain of residents have shared their view and their research with a generation eager to understand this higher plane. The space station is a symbol of humanity at its best, a shining example of international peace and collaboration in action. And as we turn our gaze outward still, this International Space Station is a living testament of our collective strength and perseverance, where our human curiosity prepares for the audacious efforts ahead. We continue to bridge the distances between us and prove just how much more is possible when we dream together.
So this is the space station in orbit today. That film was slightly dated because a couple of years ago it said 230 astronauts in orbit. We're now up into the 270s. I can't keep exact count. These are the people who are on board the space station today. There are 7 people living there. It's been continuously inhabited since the year 2000, when the first expedition went up, and we are up to expedition 71 right now. Usually the astronauts are in training for 2 or 3 years, some of them much longer than that, and then they get to fly. The typical mission is about 6 months long, although some have stayed for as long as a little over a year now. At least that's the record for US astronauts. It is the largest spacecraft by virtue of having been assembled in orbit. The assembly began in 1998. We didn't actually take up habitation until the year 2000. And we'll have 2 new residents going up, we hope, in about a week, when the Boeing Starliner goes up, launched by its Atlas V rocket. And the 2 are Navy test pilots, U.S. Navy test pilots, Butch Wilmore and Suni Williams. Both have been up there before. Both have been on board the space station, Suni several times. And I believe at least Suni is an MIT graduate, for those in the audience from MIT or affiliated with it. I see a lot of the work that I had done early on with the different modules. This is the U.S. laboratory, which was the focus of our work back in the late 1980s. This is an inflatable module that went up about 6 years ago. Actually, a commercial project. The commercial company Bigelow Aerospace bought the patent rights to the commercial module, and I'll come back to that when we talk about moon bases. That was something we were also working on in the late 1980s. This is what we think the Starliner launch will look like. This is the last Starliner. 2 have flown up unmanned without any kind of crew. The vehicle, this vehicle, as well as most of the vehicles today, are fully automated. They really don't require crew intervention. Computers really take care of virtually everything. And on the first flight, unfortunately, Boeing loaded the time wrong into the computer. And so the spaceship was trying to go into the wrong orbit and used up too much fuel and had to come home early. The last time it did dock with the space station, this was the return. It lands on land in the New Mexico desert on airbags. And so it makes it somewhat more reusable. So we hope to see that happen. Right now, I think the launch is scheduled for next Wednesday, a week from today. This is the space station as it appears in orbit. It's about 360 feet across, about 200 feet long. I say about, and that's because we have a variety of vehicles going up and coming home. The limited number of docking ports has really been a problem. In fact, part of the reason the Boeing flight, the Starliner, has been delayed has been in order to clear docking ports for it to attach to. But sometimes we have a Soyuz like you see here. Other times we have Dragons, and so you can add both of those on either end. There are also European and Japanese space vehicles carrying up cargo. So it's a fairly busy place in terms of traffic going back and forth. Some of the other features, it is powered by solar radiation, solar panels. The solar panels, the originals, go back to the early 2000s, late 1990s. And over time, they have been degrading. And so we have been adding on auxiliary solar panels. You can see a couple of them in this butterfly shape here. These white panels are solar radiators, and that is because waste heat builds up, particularly inside the modules. We have fluids that carry the heat away from the equipment inside and from equipment outside, and they go into the radiator where it's radiated. Inside, we use water for cooling. Outside, we use very high purity ammonia. We don't use the ammonia inside because of its deadly nature. And then on the inside, we'll talk about that in just a moment. So the size of the station is about the size of a football field, almost the same dimensions. I like to compare it to jumbo jet airliners. This is a Boeing 747, now sort of defunct. I mean, we use it for cargo, no longer being used for people because it's so old. But the space station and a fully loaded Boeing 747 are about the same weight, about 900,000 pounds. Station can go up above that when it has other vehicles attached to it. The station is 360 feet across. The Boeing jet is about 230 feet. So it's actually somewhat smaller. And then the modules, there's a Russian end of the space station, which you see here with the Russian flags. The service module, which was one of the first modules and the FGB module, which was the first module. These were originally intended for a second Mir space station. In 1993, President Clinton decided that since the Russian economy was not doing well, and the Russian space workers basically had no way of staying employed and getting paid, he sent a lot of money over to Russia, and for that, the Russians joined forces with us, and they contributed these modules, which were actually very important for the space station because they provided the control and power initially. Originally, we had a module that was going to provide propulsion and going to provide early electricity before we got the full-size solar panels up there. And so we were able to cancel that and use the Russians in their place. The service module was also the original habitation module for the space station. These other modules are on the US side of the station. They are all built in a similar fashion, all built to be carried by the space shuttle. It includes the European Columbus Laboratory and the Japanese Kibo or Hope Laboratory, which is actually the largest laboratory. This was always the same size. The US modules and the European module shrunk over the years. And this is the basic architecture of the interior. In the corners are what we call standoffs, utility runs of air and water and other kinds of effluents flow through these. And then the main equipment of the station is inside of equipment racks that are placed on the walls and the floor and the ceiling. And this was designed specifically so that if we ever got hit by a meteorite that was powerful enough to puncture the pressure hull, we could pull the racks away, get access to the wall, and repair that hole. We've never actually had to do that. We get hit by meteorites all the time, but none has ever made it through the pressure wall on the US side. So that's the basic architecture of the station and a few scenes from the interior. We do lots of work. Everybody is living up there. Each astronaut has their own personal crew quarters. They're doing a variety of different kinds of medical care, human research, physiology. They have to exercise typically 2 to 3 hours a day, each astronaut. And for that, we have, this is a resistive exercise, which serves basically like weightlifting, but we use springs and elastics in order to do that. We also have a bicycle ergometer. We have a treadmill, and we actually have a couple of treadmills. One of the problems that we ran into, and actually I was the subsystem manager when the first crew took up residence on the station, was a lot of this equipment did not hold up well at all. The treadmill, which was considered a critical piece of hardware for maintaining the astronaut health, broke down immediately as soon as the crew started using it because, number one, it was designed poorly. The running surface was a plastic or polycarbonate, and it immediately began to collapse as they were running on it. As you can see, the astronauts are strapped down, and therefore although they're not at their full Earth weight, they're typically at half to 2/3 of their Earth weight. And we didn't test it for that. And we didn't test it because at the time, back in the mid 1990s, it was deemed not critical. And therefore, they wouldn't give money for testing. And so one of the problems has been that the astronauts have had to become repairmen and they're doing a lot of repair work, which is far more intricate than anything originally planned for. And they've been able to do that. They've been able to maintain a lot of this equipment, although a good deal of it has now been replaced with much better equipment. You see a computer workstation on board. We mainly use laptop computers, and from that, the astronauts can get in to virtually any menu they need to operate any system, although usually the astronauts are not doing that. Most of the operation is conducted from the ground, and in fact, over the years, we've moved a lot of the operation out to the individual control centers in the different country. So early on, when the astronauts were operating the robotic arm, they would do it watching computer screens and manipulating it by hand controllers on board. Then we had people on the ground taking over control of the robotic manipulator. And now the people in Canada who actually built the robotic manipulator can do a lot of the actual operations. So we've moved out a lot of their activity. One of the problems we do have to face is that the astronauts are away from home for a long period of time. Therefore, they need a lot of psychological support. Communications has become very important over the years, and in fact, there's quite a bit of it. One of our problems on the Mir orbital station was that we were dependent on Russian ground stations. The astronauts were only in touch about 15 minutes out of every 90-minute orbit. Now we have almost continuous communications. We have phones on board. Astronauts can call home every day. So a lot of changes have gone on over the years. We're conducting research in a whole variety of areas. Biology and human research, earth and space science. We have facilities on board dedicated to looking at the earth in particular, different kinds of physical science and technology demonstrations. And you see one of the pictures here of an astronaut inside of the cupola. The cupola was an idea that I had come up with back in 1987, and I named it the cupola. Here you see it is the main observation deck for the space station, provides kind of a three-dimensional view. So along with all of that research, we're also developing the systems for future exploration, and we are keeping our international partners engaged in the program and developing commerce and trying to inspire kids. Although one of the sad parts of the job is so few people realize the station is up there and that the astronauts have been on board continuously over the last 20 years. But the kinds of things we have done towards exploration are to prove spacewalks to be relatively easily done on fairly short notice. We've done well over 240 of them now. The life support systems, we are closing the cycle on oxygen and water use. We're up in the high 90% range now for reusing water on board and oxygen on board, so we fly a lot fewer consumables. We are proving the habitation systems, different kinds of materials, communications and computers, new kinds of batteries, new kinds of solar power cells. And the station itself, the architecture has proven very maintainable and assemblable. A lot of flexibility in the configurations. A lot of changes have been made over the years. And we've integrated humans with machines. We have several robots, the main Canadian robot arm, but the Japanese have a robot. The Russians and Europeans work together to develop a robot. So a lot of these systems are being developed and have been important. Now, where we are going in the future, this is also part of U.S. law. And we have been told, the NASA administrator has been directed to develop a sustained human presence in cislunar space or on the moon, and to promote exploration, science, commerce, and basically move what we have been doing and what we have been developing in Earth orbit to go to the moon. And you see some of the systems for doing that over here. The Space Launch System rocket is based on components from the space shuttle. It carries a vehicle similar to the old Apollo command module called the Orion, and it was test flown about a year and a half ago. We are developing right now the modules for a new miniature space station, much smaller than the International Space Station. It will be placed in an orbit, a very distant orbit around the moon. And you've been hearing a lot lately about SpaceX developing a new vehicle called the Starship, and that will be the first moon lander that we use to take astronauts back to the moon. And we expect the Starship to be tested out with a first moon landing, not with people, but an unmanned test flight as soon as next year, with people to follow short time later, maybe perhaps a year after that. So in a couple of years. And we are going to the moon for discovery, but also for economics. We are trying to move and develop a space economy that extends to the moon and establish a permanent community on the moon eventually. So these are the space vehicles that are being used today. And we use unmanned versions of the Soyuz called Progress for cargo. We have used in the past a European Ariane transfer vehicle. It is no longer being developed for space station. The same people who made that ATV are now making the service module for the Orion. Japanese HTV, and they have upgraded it a couple of times, is used for cargo. SpaceX Dragon, the Northrop Grumman Cygnus, and the Dream Chaser that will come online hopefully later this year. And then the human spaceflight vehicles along with the space station, Soyuz, the manned version of the Dragon, which has been used now for a total of 13 flights and which will continue to be used. And then the Starliner, which we hope will be used starting this year. And typically, the Soyuz carries 3 people. We've been putting 4 people on the Dragon, and the plans for the future are 4 people on the Boeing Starliner, although both of these vehicles, both Dragon and Starliner, can carry 7 people. But initially, we'll just use it for 4. The rockets to put these vehicles in orbit. In the 1960s, these were the vehicles used for Mercury, Gemini, and Apollo. I'm missing a Saturn 1B in there. I had never noticed that until now. For the space shuttle, we've had quite a variety of vehicles. The space shuttle, of course, was the main vehicle for launching the US and European and Japanese and Canadian parts of the station. The Russians have used a large vehicle called the Proton, smaller Soyuz vehicle, basically the same vehicle used for Sputnik and for Vostok in the 1950s and 60s, still being used for Soyuz. The European Ariane, the Japanese H2, the SpaceX Dragon, the Antares, which has been used to launch the Cygnus, and now the Atlas V that will be used for the Starliner. And then in addition to these vehicles, we're developing these new vehicles. Falcon Heavy has already been used several times. not for the space station or not for Moon and Mars yet, but that is the intent. The Space Launch System, the Starship, and then Blue Origin, the Bezos company, is supposed to come online with a vehicle called the New Glenn, perhaps as soon as late this year. Now, actually, these are all of the moon rockets that have been developed over the years. And you see the Saturn V, the Russian or Soviet N1, which was about the same size as the Saturn V. Saturn V worked great, and we talked about the power and magnificence of it. But the Starship, which has already been launched 3 times from down here in Texas, down at the very southern tip of Texas, is larger and more powerful than any of these other vehicles. And there are plans for advanced versions of the Starship, the Blue Origin vehicle. And in addition, there are plans for an advanced version of the Space Launch System. And the Chinese have announced that they are intending to take people to the moon by 2030. And so they are developing new rockets. This one, the Long March 10, has actually been flown, but Long March 9, which is their larger vehicle, has not yet been tested. So let's talk about the future. These will be the systems that will be used for the Artemis program. Artemis is a program that will initially take people to the moon. Unlike Apollo, we will be continuing to go to the same place on the moon and set up a base near the South Pole of the moon, because the South Pole seems to be where there is frozen water locked up. We have to go and find it first. So that's one of the things we're going to be doing, is prospecting for water. The Orion capsule, which will carry usually 4 people. And you see a comparison of the Orion with the Starship lander. This is the Starship Moonlander. Starship was originally designed to carry as many as 100 people. It's kind of the jumbo jet of spaceships. And in about 2 or 3 years, we hope that we will fly a mission called Artemis 3, in which the Orion will carry astronauts. It will link up with the Starship, which will land on the moon. We're also developing new spacesuits to replace the ones that have been used on space stations since the very beginning and since the beginnings of the space shuttle. We're developing a new space station called the Gateway, with a series of habitation modules, power and propulsion modules. Talk a little bit more about that. Blue Origin is developing a smaller lander called the Blue Moonlander. The Japanese are contributing a rover, which they've called the Lunar Cruiser, and it is being built by Toyota. This is an early sketch of it. I don't think it'll come out looking like that. I'll talk about that in a moment. And then the rockets that will be used to launch these vehicles. This is the Orion capsule, and there are 4 astronauts. Next year, we hope that the Orion will be launched on Artemis 2. Artemis 1 flew a year and a half ago, and it tested the vehicle by sending an Orion capsule around the moon, stayed there about 10 days, and then came home, and seemed to work fairly well. There's a few problems that they are still working on. But Orion 2, right now scheduled for late next year, 2025, will carry these 4 astronauts, and they will be able to loop around the moon, similar to Apollo 8 back in 1968. This was the launch of the Artemis 1. in November of 2022, year and a half ago. The escape tower separation, the stage, and then the vehicle separation from the vehicle. Went out to the distance of the moon, 240,000 miles, went into an orbit around the moon, then came home at about 25,000 miles an hour, came through the atmosphere okay. And initially, the atmosphere has a braking effect. Then it comes into the atmosphere, and we use a series first of drogue and then main parachutes in order to land the vehicle in the ocean, where the U.S. Navy picks it up. Now, the Starship is the next piece that needs development. As you are seeing, we are launching it. It's gone through a series of tests over the last 5 years. They have actually tested the lander part, the part that is supposed to come back to the Earth or land on the moon. It has been landed in a soft landing on Earth, the last time successfully. And in fact, landing on Earth is more difficult than landing on the moon because of the gravity. And we expect that this is the main vehicle that we will be used first for moon landings and eventually for Mars landings. Some of these are very old drawings. This has been on the books for about 10 years and in development, as you can see, since about 2018. And this is the vehicle as in its moon lander version, as we expect it to land on the moon. Now, a little bit about the size of this vehicle. Once again, our Boeing 747, about 230 feet long, and about 21 feet is the diameter across the main fuselage. Starship, this is just the lander part, doesn't include the big booster, is 160 feet and 30 feet in diameter. This vehicle is the largest spacecraft ever launched in a single piece. The last flight successfully made it almost to orbit, didn't quite make it into orbit because it wasn't designed, although they basically had the velocity and could have made it into orbit if they had wanted. But this 30 feet, the largest diameter module we ever launched previously was Skylab. It was 23 feet, just a little bit bigger than a 747. So this is a very large vehicle. And a little bit more about it. This is mainly the last launch, which I went to see. Quite impressive. Not just the size and the noise, but the pressure that you felt from the thrust of this thing at about 3 miles was very impressive. They had some problems on the first 2 launches. This was the staging. You see the engines shut down in sequence, the stage separation. It was intended to return back to the ground to land near the launch pad on future missions. The Starship in the future will go first into orbit and then to the moon in order to conduct the moon landing. And we'll talk a little bit about that in just a moment. And one of the comments in the chat says it looks kind of like a sci-fi version. Actually, a lot of what Musk does is to make it look like that. For instance, they didn't think originally it looked pointy enough. They added a little bit more length to make it pointier. Musk has proposed that it could be used as the basis for a base on the moon, lie it down on its side, cover it over, with lunar soil, with lunar regolith in order to protect it from solar radiation. The kind of solar storm that we have been experiencing over the last few days has not been too much of a problem on the space station because it's well within the Van Allen belt, but on the moon could prove a real hazard. And you could even separate the stages. Now, this might be a good idea, although when we looked at the idea of using the leftover stage of a Saturn V, originally it was proposed to send the stage up full of fuel, and the logistics of actually clearing it out, cleaning it out, putting in all of the equipment, by the time the astronauts would have been done making those modifications, really did not make a lot of sense. And when you look at the interior of the Starship, although the lower half are the large fuel and oxidizer tanks, the upper part of the Starship is all habitable. And as I say, this is a big vehicle, so you could put things like the large Toyota Rover on board. There will be lots of room for the crew on board, and we'll see a little bit of that in just a moment. The Starship is about 160 feet long. This is kind of how the interior might look if it was a large open volume. It has a total of 6 main engines. The main engines are used to get to the moon, slow it down, and orbit around the moon. Now, on Artemis 3, which will be a year or two after the flight next year, and Orion will meet up with the Starship. 2 astronauts will transfer on board the Starship, and the Starship will begin its descent. In order to reduce the amount of dust kicked up during landing, they don't use the main engines. They'll use smaller engines up on the upper part of the vehicle to lower it softly. And once they get there, they have a door that will open and an elevator that comes out, and the astronauts descend by elevator from about 100 feet up to walk on the moon. First time we will have walked on the moon since 1972. Now, we had a rover developed for the Apollo program. This is it in operation. Had a top speed of about 10 miles per hour. And we have a contract now to develop a similar kind of a rover, but the big pressurized rover, kind of an RV on the moon, is what the Japanese and Toyota are working on now. And on my shelf over here, I have one of my little Japanese-built die-cast figures of this cruiser. And one of our main goals is going to be to harvest materials on the moon, oxygen and water. And we think we will lay down pipes to actually take the oxygen and water from its source to the lunar base. There are plans to develop a lunar base over the next 75 or 100 years. The spacesuits that are in work right now by Collins Aerospace and ILC, which was the company that made the Apollo and the Space Shuttle spacesuits, we hope will be a little bit more easily maintainable and will stand up to a very coarse lunar material. So that is the next step, is the Starship and making sure it can land on the moon. The step after that, Artemis 4, is to build and then inhabit this space station. The space station is called the Gateway, and it will be composed of a series of habitation modules, a power and propulsion module using solar electric propulsion, the landers, either the Starship or the Blue Moon lander, and logistics vehicles that will be based on the current Cygnus and SpaceX Dragon logistics vehicles. And they're coming from a lot of different countries. Now, the Gateway goes up into this high rectilinear halo orbit around the moon. It will come as close as perhaps 1,000 miles, but head out to about 40,000 plus miles. This orbit is more easily maintainable, doesn't require much fuel to maintain, plus it provides continuous communications with Earth. The big problem is the lander has to get from 1,000 miles down and then go up to 1,000-mile orbit in order to get back. We've had this satellite called the Capstone in orbit for several years, testing out the orbit and the propulsion system. The Artemis 4 mission will begin with a power and propulsion and one of the habitation modules. And then we will send up an Orion capsule with another habitation module. And more modules will be added over time. The third major piece to be added is the robotic arm. These are relatively small modules, only about 9 feet in diameter. That compares with the 15-foot International Space Station modules. So it'll be a fairly small space, bigger than the Orion capsule, though. And then the last big piece that will be brought up is the United Arab Emirates airlock that will assist if the astronauts have to go outside from the Gateway. And then the logistics will be carried up, as I mentioned, by extended versions of the Cygnus and the Dragon, the SpaceX Dragon, launched by the Falcon Heavy booster. Now, the modules for this space station, for the Gateway station, are being manufactured by the Europeans and by the Italians, and the airlock is being manufactured by the United Arab Emirates. So quite a bit of the space station comes from other countries. And it kind of shows the progress in space commerce over time. And the Starship as it departs from the Gateway. The same company in Italy, together with the European Space Agency, is building a lot of our modules over time. The original Space Lab modules that went into the shuttle. They built the Space Hab modules, both the smaller single and the larger double size module. They built the European Columbus Laboratory. They built the logistics vehicles and Node 2 and 3. They built the cupola, the observation deck, and they built the Cygnus logistics vehicle for the station. So although a lot of these are worked in collaboration with U.S. companies, the actual manufacturing is going on in Italy. This is the Artemis plan. So in about a year, year and a half, late in 2025, the Orion capsule will take the 4 astronauts around the moon. And Then after that mission, we will use the Artemis, the Orion capsule together with a Starship moonlander to land on the moon. And then after that, build up the Gateway station. Now, when we talk about doing one of these missions, it's not just a launch of an Orion and the launch of the moonlander. The moonlander gets into orbit basically depleted of fuel, and it will take something on the order of 10 and maybe more than 10 more Starship flights in order to fill it with fuel and oxidizer for the moon trip. So it's really each one of these expeditions to the moon, when it involves a Starship, is something on the order of 10 or 12 flights. Now, these Starships are supposed to be reusable, and that's one of the things that SpaceX is trying to prove over the next year. So we will send the moonlander up, send up a series of Starships to refuel it. Once the moonlander gets into orbit and is ready to do the descent to the moon, then we send the Orion up on an SLS rocket with the astronauts. Initially, just 2 astronauts will land, but on later flights, perhaps more astronauts. And we've been developing what are called the Artemis Accords with countries around the world. I think there were a couple of more signatures in just the last week. So I think we're up to about 40 countries that have now signed up to this. But notably, the Russians and the Chinese have not signed on. They are intending to do their own moon base separate from the one that the US is leading. I showed this slide earlier. These are the new rockets that will be developed for these missions, compared with the Saturn and the N1, which were the rockets developed back in the 1960s, and the new Chinese rockets that are in development for landing their taikonauts, their people on the moon, in about another 6 years. And a comparison of the vehicles to land. This is the Apollo hardware, which any of you who are old enough to remember Apollo were pretty familiar with. The mission is considerably different because the Apollo command module, after Apollo 11 or 12, it would go into an orbit only 10 miles above the moon, and it never went into an orbit much above 100 miles around the moon. The Starship, the Gateway, and the Orion all go into a much higher orbit, between 1,000 and 40,000 miles. So it's a little bit different kind of a mission, uses a lot less fuel and propulsion. This was the hardware that was developed for the Soviet program, a forerunner of the current Soyuz, called the Lunar Orbital Compartment. The lunar compartment would carry 1 astronaut down to land on the moon, and there was talk of a Lunicod, which was their unmanned robotic rover, would be used in conjunction with these missions. Never worked, and after 4 separate problems, the vehicle never launched successfully. The Soviets canceled the program, and parts of the vehicle are strewn around Kazakhstan mainly today. I was among the first Westerners that was allowed to get up into the lunar cabin. There's a couple of those still remaining. The future Chinese vehicles, the Mengzhou, which is their orbital capsule, and the Lanyi, which is their lander. So their landing, at least initially, is going to be much more Apollo-like, and then eventually they will expand a base on the moon. They just launched within the last week an unmanned vehicle to land on the backside of the moon, first time that has ever been done. And then the hardware for the US and U.S. international program that we've talked about already. This is the Blue Moon lander. Now, several years ago, I was involved in designing a moon base. This was based on a space station module, so a 15-foot diameter cylinder. And this module was more like the Japanese module in length. The US modules were cut back from about 45 feet to about 27 feet because the shuttle could not launch the larger module into the high inclination orbit. You'll notice that one thing, when we build a pressurized module, it generally comes out looking like a cylinder in order to distribute the pressure. This was my version of a moon rover, again, a cylinder. And so I'm not sure that the Japanese module or that the Japanese rover will have that boxy SUV shape as they are showing today. And so they have to mesh their aerospace engineers with their automobile engineers, and working in a vacuum environment is going to be a little bit different. This was my idea for a moon base back in 1989. It was a large inflatable sphere, and we actually tried here at the Johnson Space Center to build this full scale. And when they got into it, they didn't know how they would actually build it. Now, it's a little bit more difficult in a 1G environment, and they looked at a different design, which they called the transhab, which centered more of the hardware on the center core, and then it inflated around it, and then the hardware would be moved out. That transhab was patented, and then Mr. Bigelow, who wanted to put hotels in orbit, bought the patent and has flown a number of those modules, one of which is attached on the space station today and seems to be doing just fine in terms of the design of the vehicle. Now, although we will be doing a lot of science on the moon, a lot of what we're going to be doing is prospecting mainly for water, at least initially. And the intent is to set up a permanent human presence that will be the first place that we ever are able to do that beyond the solar system. And our intent is to get people back to the moon in the next 2 or 3 years. We're very dependent on SpaceX and that Starship, and start setting up the Gateway Station a couple of years after that, by the late 2020s, and then the moon base after that. And that was, I think, all I had to tell you today, and I'm over on time. So let me ask if there are any questions.
That was really fantastic.
Thank you very much, Gary. You're not over on time from our perspective. It's really your time that.
I have an open-ended time frame, so.
Good. Now I know there were some comments in the chat. Do you want to do the chat questions first before we do back and forth in real time?
Yes, I do. I did not have time to really look at it while
Nor did I.
But
do you want to look at them, or do you want me to what?
Well, why don't I try to step back through them? And so for the Gateway Station, isn't getting into a rectilinear orbit very expensive, or is there some neat trick? Actually, the reason that this orbit was selected is because it is a very low energy orbit. I don't have the proper graphics to display it. We typically show an orbit as just a long elliptical shape. This orbit is long and elliptical, but keep in mind it goes about a quarter of the way back to the Earth, although it's going north and south. It's not going in the direction of the Earth. And the idea is to not orbit around the mass of the moon, but to orbit around the Lagrangian points that are out at some distance from the moon. That makes it much less expensive in terms of continuing fuel or continuing propulsion to keep it in an orbit. Now, getting into the orbit that gets you there takes somewhat less energy than if you get into the much lower Apollo orbit. Now, keep in mind, Apollo was over-designed because at the outset of the Apollo program, they did not know if it was the Apollo service module that was going to land the astronauts on the moon, or eventually they went to this lunar orbit rendezvous, which used the Apollo lunar module, much smaller and lighter vehicle to get down to the moon. So we had an excess of propulsion capability. We do not have that on the Orion capsule. The service module of the Orion is based on the European ATV cargo vehicle. The main engine on the Orion is a space shuttle maneuvering engine, one of the orbital maneuvering system motors. And so it does not have enough propulsion, either in terms of thrust or fuel, to get into a much lower orbit. So if we ever had to go down and rescue astronauts, for instance, this vehicle cannot do it. Perhaps a future modification of it would be better for that purpose. But no, it takes less energy. As far as kinds of propulsion, the Gateway itself does use a solar electric. So it uses solar panels, and it converts the solar panels into photons, and those photons are mainly what is used for the main maneuvering in lunar orbit. This is a technique of propulsion we've really used on quite a number of vehicles already, unmanned vehicles. The small vehicle, the Capstone vehicle that has been in orbit since 2022, is using that propulsion technique in the same near rectilinear halo orbit to keep it in orbit there. It was actually, that was the intent of that mission. Does the propulsion system work, and can it maintain that orbit with so little propulsion capability? And so it seems to be working out fine. So yes, there are new kinds of fuels, new kinds of propulsion for these vehicles. And we are using non-chemical propulsion.
Thank you.
And how do you provide water? Is some of it provided from fuel cells? I believe the Japanese are looking at fuel cells for their life support system inside of the rover. They're also looking at using hydrogen that could be captured from the solar wind, or distilling the lunar rocks. And in fact, in the video, you saw somebody loading some of these modules that would carry some of the fuel. But so fuel cells are being looked at. Now, in terms of how we have done it on space station, space station does not have fuel cells, but it does have a closed loop environmental control system. And I'm trying to find, I do have a slide that shows this. I have a lot of other slides. Getting to them quickly is a problem. One of the problems we faced on the space station in the wake of the Columbia accident in 2023, without the shuttle, we had a lot less capability to bring up supplies. And so we had to reduce the crew, went down to only 2 people, and we had to reduce the supplies. This was the curve. So every time there was a logistics vehicle that carried up fresh supplies, you'd see the consumables increase, then it would decrease. And so one of the problems that we ran into was water. Water is by far the heaviest thing that we bring up to the space station for consumables to maintain life. And so on board the station, we have a series of racks, and it takes the urine and other wastewater and it distills it out. It goes through a series of purification beds, a series of ovens that bakes out the material. Now, initially, this did not work quite so well because we hadn't taken into account how the equipment needed to work. We were fully aware for many years that as an astronaut stayed in orbit, his bones demineralized. And so he was suffering from a situation that looked kind of like osteoporosis. And we saw the minerals coming out in the urine, in the waste. And the people who were designing the environmental control life support system did not take that into account. And so early on, as the wastewater would go into this system, we would form we called it a urine brickle, kind of a peanut brittle type, and it clogged up everything. And the astronauts would have to take it apart and clear out holes and so on until we figured out what it was that was clogging the system up. And so we had made some modifications over time, and this system works very well now. It provides capability, as I mentioned earlier, to reuse about 90. A couple of years ago, it was at 93%. I've heard higher numbers of 95, even 98% now. So we take up far less consumables, far less water, far less oxygen coming out of the system. If you can make it out here, you see the different materials. So basically, the astronauts say they drink their coffee, they go to the bathroom, and then a little later they re-drink the water that came out. And it's actually cleaner than your tap water at home. So, and in fact, this system has been miniaturized and is now used in some parts of the country, war zones and so on, in order to process water. So we've actually done a pretty good job in being able to reuse that so we can carry far less material. And let me look for some more questions. Is up the same direction throughout the ISS? When we designed the ISS, as I mentioned, the Skylab astronauts were our consultants. And they said, what we want is a definite floor and ceiling orientation. Further, we want the floor oriented towards the Earth, which we thought that was kind of interesting. Why do you need a floor oriented towards the Earth? But they really like to maintain constant orientation. And so that was the original intent, was in the space station, in the International Space Station. Every module would have a floor and ceiling kind of an orientation. And we would try to maintain that throughout. Now, it hasn't become 100% possible, because when we bring in modules at right angles going down or up, then sometimes the orientation changes. So we do have a local vertical orientation. Most of the station predominantly has a constant floor and ceiling orientation. But it was something that we consciously designed in from the start. And we use other cues as well. For instance, I talked about the utility runs running through the station in the corners. For instance, airflow, the fresh air goes through the vents that are located in the two top corners. And then the return flow brings the old air in through registers in the lower corners of the station. So airflow provides a cue. Also makes it very convenient if you lose something, to go look at the filters for the return register. That's probably where you're going to find it after a while. And yes, SUNY is from Needham, and so that's why they named a school after her. The U.S. military space station, I did not mention it, but if you did record this, you can go back to my early slides. I'm afraid to do that right now, because if I try to go back to my slides, I may disconnect from the meeting. But I did have a picture of the manned orbiting laboratory. Beginning in about 1963, the Air Force primarily was developing a space station called Manned Orbiting Laboratory. It actually goes back to a program that was at least developed to use the Atlas missile. And after the missile got into orbit, you would be able to clear it out and use the missile as the living quarters. And so that was the origins of Manned Orbiting Laboratory. Beginning in 63, it was going to use a Gemini capsule. And they got all the way to the point of flying an unmanned mission in 1966 of the Manned Orbiting Laboratory. They had to prove that there was a hatch in the heat shield of the Gemini, that the hatch could be resealed and the Gemini could still make it back through the reentry, the high heat, and land successfully without roasting or vaporizing the astronauts on board. And so they did prove all that. And they flew some experiments on that first unmanned test. And then in 1969, the program was taking an awful long time. Originally, it was supposed to go into orbit around 65 or 66. In 1969, just about the time the first astronauts were landing on the moon on Apollo 11, NASA had told Congress and the president that they wanted to use the last Saturn V for the Skylab mission. And so Congress, in their budget exercise, basically curtailed the military program and consolidated it with the NASA Skylab program. All the younger Air Force astronauts were allowed to come over to NASA, even though they were told, we have no flights for you. Flights were running out by that time, and all the moon missions were basically spoken for, and there was nothing until the shuttle that would start about 10 years later. So a lot of the mole astronauts became NASA astronauts, including some of the more famous ones, Bob Crippen, who flew on the first shuttle mission with John Young and Bob Overmyer, and even some of the scientists, mission scientists, came over from the Air Force at that time. And I'm not sure if I missed any other questions in the chat.
I asked about space elevators.
You're talking about not the elevator on the Starship, but an elevator to actually lift people off the Earth and take them into space. I mean, it's a concept, never been proven that you could really do it. I have my doubts that you could do it. You have to keep in mind all of these things up in orbital space are not just hanging around up there, they're staying in orbit by traveling at fairly high velocities. You'd have to go a long ways out before you could maintain a position over one particular place on Earth. So you're talking about going out into a geosynchronous orbit, which is 22,000 miles. It's a pretty long cable to be able to lift things that way. Now, they did try an experiment on the space shuttle where they deployed, I guess you could call it a sub-satellite. It wasn't supposed to detach from the shuttle, but it was on a cable. I don't remember the exact length, 150 feet or so. And on the last test of it, there was such an electric effect on the cable because of probably due to static electricity. I don't really know all the details. And the cable was cut and the vehicle was lost. Called the tethered satellite system. And a couple of MIT grads were involved in that, including, I think, Franklin Chang Diaz and Jeff Hoffman, who's still a professor at MIT. So the idea has been proposed.
The alpha magnetic spectrometer, that little cylindrical blob on the ISS, has collected, as of apparently this morning, 275 billion cosmic rays and analyzed their energy and potentially their mass for the ones that are not protons. There are cosmic rays that are very, very energetic, not seen necessarily by the space station. But does NASA have any kind of a plan dealing with the potential of these things that can literally have the energy in a single proton of a major league fastball?
Well, one of the reasons for AMS was to actually try and do the research to figure out what are the energies of these particles and how many are there, and what is their distribution and so on. I don't know that they've gotten all the results out of AMS that they had hoped for, but it when we talk about the international program of ISS, AMS involves many more nations. I think something like 45 or so. I was involved a little bit with it, with Sam Ting and the people who were developing it back in the late 1990s. We are facing problems in the future. If you talk about a mission to the moon or you talk about a mission to Mars, we know that there are different kinds of things, including cosmic rays and including meteorites and so on, that are going to hit. They are out there, and you do need protection against. On the moon, as we showed in that moon base picture, they're talking about using lunar soil built up around the habitat in order to protect astronauts. On a mission to Mars, they have talked about a water jacket. So all the water that you're carrying with you would go into tanks. If it's a cylinder that you're living in, then it would be a toroidal tank that would surround the living quarters. They've also looked at things like developing, you could call it a force field, an electromagnetic field around that might be able to deflect things. So that has been talked about. May require more energy than a simple solar cell. So there are a variety of different ways that has been discussed, but we do know that it is a problem for the future and for these long duration missions going long distances away from the Earth. Right now, in lower Earth orbit, we're relatively protected on the space station. We see a lot less of this. Although, even on the space station, when we get a major solar event, we have on occasion had to tell the astronauts to take refuge in some of the denser areas where they do get a little bit more protection. And that happens, last I checked, on the order of about once a year that we have to tell them to actually go into one of their safe haven areas.
Yeah, I have two questions, really. The first one is that since the moon's surface is very rough and you're going to have very, very large, long rockets, how's it going to be stabilized upright when it lands?
That is a problem. It's especially been brought up recently because two of the last moon landers earlier this year, one of them was actually supposed to come down, and then as it landed, it was supposed to actually lean over on its side. It wound up upside down on the moon. That was a Japanese lander called the Slim Lander. And then another one, the Intuitive Machines lander built here in Houston, it basically fell over and toppled over. So they're both much smaller, but still they were long, tall vehicles. And so it could be a problem. Now, keep in mind, our intent is, first of all, to be going back to the same place on the moon repeatedly. Not like the Apollo missions where we went to 6 very widely scattered places on the moon. We're going to be focusing all of our effort in one area on the surface down towards the South Pole. We're also going to be landing at least one, perhaps more than one, automated starship before the manned vehicles start flying. And so it's possible they can scout out an area, and you put in a landing beacon so that the vehicle is brought to the appropriate place, and hopefully we can find a good smooth place where they could land on, and building the actual landing legs and landing feet in such a way that it is stable up to a fairly high inclination. In the case of the Apollo lunar module, one of the reasons why it had those wide legs was in order to handle that. We didn't know at the beginning of Apollo just how rough the surface was and if there were smooth areas. And so the Apollo legs could handle an inclination of close to 45 degrees. Now, you have to actually launch off in such a manner that you have to immediately upright your vehicle. But still, there was a lot of capability to land on a high inclination surface. So it is a problem that people are aware of, and they will have to figure out a good place to bring the vehicle down, not only on the first manned mission, but even for the unmanned missions.
And can you comment, you talked early in your talk about the design lifetimes. Can you talk a little bit about how those things are worked out?
I didn't understand you exactly. The design
lifetimes.
Oh, lifetimes?
Yeah. Can you comment on how those are worked out?
Well, if space station and even the Mir orbital station are any example, the Russian modules were really designed, so they said, for a lifetime of about 5 years. But Mir lasted from 1986 until 2001. So that was a period of about 16 years. And there was not much degradation in capability. Keep in mind, it's not like an airliner. Modern airliners, every time they fly, are typically going from the full atmospheric pressure of the Earth's surface to an altitude of about 40,000 feet or so. And they go through that cycle thousands of times in a lifetime. That weakens the pressure vessel, which is their main concern. On space station, they're flying at a fairly constant, very low pressure. I mean, they're flying in what is basically a vacuum. So they're not going through those kinds of pressure cycles. They do go through a cycle of heat and radiation from the sun every time they go from night side to dark side. And so that is the main kind of life time that they are concerned about. In the case of the space station, originally the design life was supposed to have been 15 or 20 years. In a so-called cost-saving move, they reduced that to 5 to 10 years. Every few years, we do analyses. NASA has Boeing, who built a lot of the modules, or the Europeans who built many of the modules. They go through and do an assessment and analysis. Are we experiencing any problems, and can we extend the life? And so, of course, now the station, some of the modules go back to 1998. And right now, our plan is to go at least to 2030. Now, a lot of people say, oh, well, the station's coming down in 2030. No, not really. The U.S. government works in 6-year budget cycles. And so the reason why we talk about 2030 now is because it's 2024. And so we know that Congress has basically said we'll continue funding through at least 2030. As of a couple of weeks ago, when the head of the program, the associate administrator for space ops that has responsibility for the station, has said, well, in 2030, we'll begin assessing whether any of these commercial stations are real and whether they're going to happen. And if they are, then we might think about bringing the ISS down. But if not, we might just plan to keep it up there a few more years. And every few years, they go through and do this assessment and say it's good for another several years. Now, one of the Russian vehicles had an air leak a while back, but it was, I believe, determined to have been somebody on the ground inadvertently drilled a hole that had been covered over initially, but then the hole was uncovered, and that's where the atmospheric leak was happening. The Russian modules are not built the way the US modules are. There's no racks that you can pull away. You have to actually get behind equipment in order to reach the pressure hull. And so, for instance, when the Spectre module was hit in a collision with an out-of-control Progress vehicle back in 97, I think it was, it came along and it bent one of the solar arrays and the gimbal the solar array was on, and we think that was where the main leak was. The astronauts could never access it, and so Spectre lost all of its atmosphere and could never be repressurized. So it's all of this business of the modules and making sure that they maintain a livable environment gets a fair amount of attention. So far, at least, we haven't had any serious problems after 20 plus years of operation.
Are there any embryology experiments being done on the space station? And if so, what kind of results are they getting?
I believe there have been. I don't know the detail behind it, but I believe we have flown up different kinds of embryos of various creatures, including small animals, and not real mammals, I don't believe, and also fish. And so they have looked at how they progress. I've not heard of any real seriously different findings. I don't think that they progress a lot differently.
How will the ISS eventually be safely retired?
Well, the original plans were for a Progress or more than one Progress spaceship to be used to help deorbit it. You'd probably have to use a few of them. Now, keep in mind the station is falling all the time. It typically falls on the order of a fraction of a mile every day, and it has to be boosted back up. So for some rendezvous, if we're sending a vehicle up to rendezvous with cargo or crew, we may actually let the station come down. Usually the minimum altitude is no less than around 215, 220 miles, but then we will boost it back up to about 240, 245 miles. So you can take that into account in terms of letting it come down. You really get into the effects of aerodynamic drag when you get down around 100 miles or a little less than that. And so when you let it fall down, you could use the Progress if the Russians are still involved with the program. There's also a potential you can use some of these other vehicles. The SpaceX Dragon was never really planned or optimized for doing those kinds of boosts of the station, but it could be outfitted to do it also. But basically, you would use some of those logistics vehicles to further slow it down and try to control the reentry, try to guide it to the middle of the Pacific Ocean or someplace like that.
Would it come down in one piece?
They would not take it apart initially. They would leave it all together. But as it entered the atmosphere, yes, it would start coming apart into pieces.